Hello friends, welcome to Scienceteen. In the last lecture, we discussed about the three arrows of time suggested by Stephen Hawking in his book A Brief History of Time. But the actual idea was conceived much later in the year 1927 by the British astrophysicist Arthur Eddington. Arthur Eddington put the concept of one-way direction of time or the asymmetry of time, which is a unsolved general physics question, which can be understood by studying a system of atoms, molecules, and bodies around us. This one-directional arrow of time can be drawn on a four-dimensional relativistic map of the world, which we use many times while studying special theory of relativity. Physical processes happening around us can be studied in two categories. One is microscopic and other is macroscopic. So let's study these processes. So a physical process is of two categories. One is microscopic, another is macroscopic. So these microscopic processes are time symmetric, are mostly time symmetric. Apart from a few, most of them are time symmetric, and these macroscopic processes are mostly asymmetric in time. So, what do you mean by a process being time symmetric or time asymmetric? So, let's study this. In the simplest manner, we can say that if we make a video film of a process happening and play the video in forward and backward direction, then there will be no difference when we play it in forward direction and in backward direction. So both will be realistic in nature. You will see that both will seem to be realistic in our world. You will not find any strange thing happening, but the processes which are not time symmetric seem to be non-realistic when we play it in backward direction. So let's study this by an example. So the first example will be of gravity. Gravity is a time symmetric, time reversible or time symmetric force. So let's start with gravity. The first is gravity. So to understand this, take an example of a stone which has been thrown upward. So this stone will go and its speed will reduce, and up to a maximum height the speed will become 0. So u and the v will be equal to 0. Now after that it will return. So it will come back to the same point on the ground or anywhere from where you were throwing it upward. Now if you make a video of this process, so you will find that when you play the video in forward direction, you will find that this stone is going upward then downward. Now play the video in the backward direction. Now at any point in its path, let's this point, when you are playing it in forward direction, it is going upward, and from the same point it will also be going downward when it will return. So when you play the video in the backward direction, you will find you will not be able to find the difference whether you are playing it in forward direction or backward direction, both will seem to be real. It will go up and down in both the cases. So we will not be able to differentiate between the forward or backward. Now take another example of friction force. Second example is friction. So suppose, before that we will take one more example of gravity. Okay, just take a pendulum, and there is bob. Now the pendulum is oscillating from mean to extreme position, and if you again make a video of this, you will find that whether you play in forward direction or backward direction, you will find no difference. Both will seem to be real in our world. So these two processes are time symmetric. After you have played the video for some time, you will not be able to differentiate whether you are playing it in forward or backward. You can ask your friend to play the video in forward or backward, and just ask you, then you will not be able to say. So another example is friction. So there is a surface and we have a block of mass. Now this block of mass is moving with some initial velocity u, and the surface is rough. There is some friction coefficient mu. Now after some time, this block will come to rest. So V will become 0 and it will be at rest. Now when we play it in forward direction, when you are playing this video in forward direction, you will find that there is no problem. The mass is moving with some initial velocity, and due to the friction force which is acting in this direction, the mass is retarding and finally its velocity is 0. So everything is real in the video and in our real world. Now play the video in backward direction. Now this block was at rest and there was no external force acting on this block, but as the video plays in backward direction, the block will move in backward direction without any actual force. There is no force which is acting on this block in this direction, in the opposite direction, but the block will start from rest to the final velocity u at this position. So in reality there is no force acting in this direction, but in the video played in the backward direction, you will find that there is some force which is acting in backward direction. This force will not be a real force. It will seem only in the video played in backward direction. So here you will find that these examples replicate the same reality in the forward and backward direction. This both seem to be a real phenomenon, but for the case of friction, when we play it in backward direction, it does not seem to be a real phenomena. So we can say that the force of friction is asymmetric in time, but the force of gravity is symmetric in time. So our basic definition, or you can say that the basic difference of time symmetric and asymmetric is working, that is, just make a video and play it in backward direction. If you find something strange happening, then the process and the forces involved are not realistic in nature. So in the year 1927, Arthur Eddington conceived the idea of the directionality of time or the asymmetry of time, and he found that there is no analog of time, similar analog of time in a space. In a space we can move forward and backward, but these things are not found in case of time. In time we can only move in forward direction, not in backward direction. We will find that in some microscopic processes, in the case of particle physics, we have time symmetry, but in most of the macroscopic processes we find that going backward in time is not possible, and this thing was conceived with the idea that entropy is not a time symmetric quantity. So entropy is not time symmetric. So the arrow of time is defined as the decrease in the available free energy. So free energy is the energy available in any thermodynamic process which can be converted into useful work. And in the next year, 1928, Arthur Eddington published his book, The Nature of Physical World. What he said can be understood by a small problem. Just take, there are some molecules which are arranged in this way, and there are another molecules which are arranged in this way. They are marked with different color. So if we left it untouched, after some time when you again revisit the system, you will not find this in the same order. It can become like this. After some time has been elapsed, you will find that these are arranged in any manner. So you can just count and arrange them. So as the time elapses, this order vanishes, and disorder comes into picture. So as time passes, this order is lost and disorders comes into picture, and after some time we can say that a kind of equilibrium has been reached between these random motion of the molecules. There will not be such an order after we'll wait for long enough. So he said that going from past to future, there is some increase in random element. Increase in random element increases. And he also concluded that this randomness cannot be reversed or removed from the system by its own. It can be done, but it will be very difficult to do it. So he concluded that this randomness cannot be undone from the system, and the times arrow is the property of the entropy alone. And time has a property which we cannot find a similar analog in a space. Time has some sort of direction, but a space, in a space we can move it forward and backward also, but not in time. This arrow of time, or the directionality of time, has been found in many processes happening, starting from the thermodynamics to the frontiers of particle physics. We find everywhere this arrow of time. Now we will discuss some of the phenomenon where we find some kind of directionality of time. So not only the thermodynamic processes or the mechanical system, this arrow of time, or the directionality or asymmetry of time, has been found in various processes happening around us. So starting from the thermodynamics to the frontiers of particle physics, we find it everywhere, in psychology also, which we discussed in our previous lectures. So we will just list some of them, not all. So the first is thermodynamic. The second is the cosmological. Third is thermodynamic arrow of time. The third is radiative. Fourth is causal. Fifth is weak arrow of time. The sixth is quantum. And the last, there can be other processes also, but these are some of them. So the seventh is the psychological. The psychological or perceptive. So the thermodynamic, the cosmological and the psychological, we have already discussed this. So we will start with the radiative, causal, and so on up to quantum. So let's start with the radiative arrow of time. Suppose you throw a stone in a pond, then the point where the stone touches the water surface, it generates ripples, concentric ripples throughout the dimensions of the pond. So here you will find that the wave, the disturbance, is moving out radially. So this kind of wave is called radiative wave. And there can also be, there is some sort of possibility for waves which are converging in nature. There are certain oscillating particles on the periphery of a circle, and these particles are generating waves, and these waves are converging on a point. The equations of wave mechanics allow such kind of waves, but in our real world we find that these kind of phenomena are very rare, and this is very common. So we can say that the initial conditions of generating a wave goes into the favor of radiative kind of wave and not the converging type of wave or convergent wave. Or we can say that the probability that the initial conditions are such that it can produce a radiative wave is much higher than the initial condition available for producing a convergent wave. So now we can say that in every radiative wave the entropy of the system is increasing. In the start of the event, only these molecules were in motion. Now after the time elapses, all the molecules present on the whole of the pond, the surface of water, is oscillating up and down, and here you will find that the wave is converging to a single point. So the disturbance here is disappearing and the disturbance in the center of the circle is increasing, but here the disturbance is starting from a single point and is spreading throughout the pond. So the randomness of the system is increasing in this kind of wave rather than this kind. So this is allowed by the thermodynamic arrow or thermodynamic laws. So the thermodynamic arrow of time will allow such kind of waves rather than these kind of waves. It doesn't mean that we are going backward in time. We can produce such waves, but the probability conditions are very rare. Or in the other way, we can say that in the first case the entropy is increasing, but for a convergent wave the entropy is decreasing, and the second law says that entropy will always increase in the arrow of time. So these kind of waves are contradictory to the second law of thermodynamics, while these types of waves are favorable for second law of thermodynamics. That is, the concept of entropy allows these kinds of waves, but is not parallel with these kinds of waves. So in the next lecture we will start with the causal arrow of time. Please like, share and subscribe to our channel, and thanks for watching.